We know from the history of astronomy that an elliptical Keplerian orbit, shown here as the dashed curve, is well approximated by a motion with the frequency around the Sun in a circular orbit and another motion with another frequency in a smaller ellipse around the original orbit. This smaller ellipse is the epicycle, and it turns out this is a very good approximation for perturbations out of a circular orbit. This approximation is called the epicycle approximation, and that's what we're going to see now. Now consider the motion in this effective potential here. R is the radial distance, and Z is the vertical. The effective potential then is given by the potential here in RZ and the centrifugal force. In the epicyclical approximation, we are considering orbits that have a small perturbation to a circular orbit that we're going to call RC. So we define the perturbation position as a small perturbation around RC, is the distance minus the radius of the circular orbit. So let's now expand the effective potential in a Taylor series around RC. That's what you have then. The constant, of course, for a potential doesn't matter. And the first derivative cancel because we are around the minimum. So we only have the second derivative, the quadratic terms. Now, these quantities are constants. They are the second derivative of the potential evaluated at a particular point, be in R and Z. The particular point in R is a position in the circular orbit, and the point in Z is the midplane. So these being constants, we can substitute, say the radial one by kappa squared and the vertical one by nu squared, so that the potential now is simplified. And these are harmonic oscillators. So this shows that the body is executing oscillations around the circular orbit. The body is executing a small ellipse around R0 and Z0 in this around the circular orbit. This small ellipse is called an epicycle. Kappa is called the epicyclic frequency, and nu is the vertical frequency. Now, to find the epicyclic frequency, let's expand the effective potential. Defining here, placing here the effective potentials given by this equation and just taking the derivative. And let's introduce omega r, which is the angular velocity of the circular orbit. So for a circular orbit, this is what we have. We have omega square r is equal to the derivative of the potential in radius, which is equal to the centrifugal force. Gravity is equal to the centrifugal force. It's in equilibrium. So if you isolate the phi dr and take the second derivative, this is what you get, because we can substitute the angular momentum also by a function of omega. So we have this expression for kappa, since we found what the second derivative of phi is. We have kappa being equal, kappa squared is equal to 4 omega squared plus r ddr of omega squared. Now, for most astronomically interesting cases, the epicyclic frequency lies between the Keplerian frequency and twice the Keplerian frequency. In fact, you can solve this equation for the Keplerian potential, where omega is equal to square root of gm to the power of r cubed, and you find that for the Keplerian potential, kappa is exactly equal to the Keplerian frequency. Now, the equations of motion for the particles that are disturbed from the circular motion are then given by these very simple equations. And these are harmonic oscillators with the solutions. So in 3 dimensions, this is what the motion would look like. We would have a circular orbit and then have the epicycle motion in x, going from the pericenter to the apocenter, and have also the oscillation in z going up and down around the midplane. A star will go through all of the space given here between these values of radius and vertical distance.